Okay, all right, so let's get going. Okay, my name is Helen Twigg. I'm the president of the National Universities of Ireland SEG Chapter and part of the Symposium's organising committee. On behalf of our student chapter, I would like to welcome you to the SEG Student Chapters Earth Day Symposium, which is a forum dedicated to reflect on the challenges and aspirations and role of the student and early economic geologists in a world experiencing rapid climate change and other ecological and societal changes during a new and hopefully green technology revolution. So today, we celebrate and honour Earth Day, an international event celebrated around the world to pledge support for environmental protection. The year 2021 marks the 51st anniversary of the annual celebrations, and the theme of Earth Day is Restore Our Earth. We geologists have a role to play in restoring the Earth. Not only are we responsible for finding the critical minerals which the world needs for low carbon technology, but because we're economic geologists, we can actively be involved in reducing the environmental footprint of our industry as well as our personal lives. So just a bit of housekeeping before we get to the business of the day or the evening, depending on where you're from. You signed up. When you signed up, there was a code of conduct that you agreed to, which can be generally summarized as let's just be respectful to one another. But if you want more details, we will pop a link in the chat box. We will also ask you to keep your mics on mute at all times. Okay. We have received a wealth of amazing contributions from the SEG student members from chapters all around the world, and also from professional geologists. And while we won't be able to broadcast every contribution during this live session, because we've got many, many hours worth of work, they are all available on our YouTube channel, which we will encourage you to watch at your own time. And the link again will be popped in the chat. This live session consists of student research presentations, followed by Q&A sessions. And then the second part will consist of a panel discussion, all of which will be accompanied with a short video montage showcasing the perspective, motivations and thoughts of students and academic geologists. If you would like to submit questions to the student speakers or panelists, pop them into the chat box. If they're directed towards a particular speaker, please start the message with their name. The chat box will be monitored by one of our members who will direct the questions to the relevant person. Okay, and these will be answered during the Q&A session, time permitting. So besides showcasing research by SEG students and discussing the challenges and opportunities for economic geologists and the discipline as a whole in the changing world, a key goal of this event is to make connections and create spaces for future collaboration. We want to shout out and give a big thank you to everyone who directly contributed and helped in many other ways to kind of get this kind of symposium together. I'm now going to hand you over to Simon Jarrett, the chair of the SEG Student Affairs Committee and also an assistant professor at the University of Nevada, Las Vegas. And he has prepared a short video for us, introducing the theme.
Hello and welcome to the Society of Economic Geologists Earth Day Student Chapter Symposium. It's a privilege to be asked to give this opening address by the organisers of the National University of Ireland SEG Student Chapter. My name is Simon Jarrett and I'm the Vice President for Student Affairs within the Society of Economic Geologists. I've been asked before I get onto the kind of main focus of the introduction on Earth Day to say a few words about the society. The SEG is an international scientific society that consists of members who are interested in economic geology, be they in industry, in academia or in government. And we have a large number of student members, including a total of 109 student chapters in 31 separate countries. And we support students and their research and other activities in various ways. The Society of Economic Geologists often gives more than $100,000 in individual research grants to students each year. We support students through fellowships during their graduate studies. We also support individual student chapters, groups of students based at different universities across the world to undertake activities like field trips, or at the moment we're running a vlogging competition to highlight interesting geology around the world that people can showcase to other students who might not have access to specific rocks or outcrops or geoscientific locations. Student membership within the society is heavily subsidized. We offer discounts on conferences, meetings, and other events, and it's well worth joining the society if you've not done so already. Equally importantly, the students are the future of both our science and our society, the Society of Economic Geologists. So being a member gives you a say going forward in how you see the Society of Economic Geologists evolving and developing. We already have give younger members a say by having, for example, early career professionals and student affairs committees, and we value the input of younger members of the society. And we've also recognized recently a need for wider discussions over diversity, equity, and inclusion. And we've set up a standing diversity, equity, and inclusion committee and expect to see more from the society in this space. Equally, I know probably quite a few of you feel strongly about these issues, so feel free, again, if you're interested in that aspect of the society and improving the society for members going forward, to get in touch, get involved. And if you're not a member already, it doesn't cost much to become a student member, and you get a lot out of it. Basically, more members from more diverse backgrounds, more inclusive the society is, the more people we have that can say and have a say on how we can make the Society of Economic Geologists a better place for all members at all levels going forward. But to shift focus slightly on the role of economic geology in the mining industry in modern society. Many would wonder why on earth economic geologists and people associated with the mining and minerals industry would be having an event on Earth Day. I'm sure, as many of you know, Earth Day is an annual event held globally on April the 22nd, since I believe 1971, or 1970 rather, with this year marking the 51st Earth Day. Events this year likely to involve more than 1 billion people in the majority of countries around the world. So what does mining have to do with Earth Day? You know, if you're a member of the general public, you would think that mining and the minerals industry is kind of the opposite of what Earth Day represents. You know, the perception of a lot of the general public would be that mining is old, it's socially and environmentally problematic, it's polluting, and it's certainly no longer needed. But of course, us as economic geologists know that certainly the latter is not the case. You know, modern society is founded on non-renewable natural resources, and the majority of which are mined and quarried. You know, that demonstrates and exemplifies the importance of economic geology to modern society. The technology you're using to listen to me talk now is essentially mined or quarried in kind of a raw level. You know, the copper to supply the electricity to your device, the battery that your device is running on, all of this has to be mined at some level, at some point. Simply put, without mining, we cannot have the standard of living that we've come to expect in the modern world. Equally importantly, and relating to Earth Day, if we're to do anything about climate change, we're going to lower CO2 emissions and prevent further damage by anthropogenic climate change across the world, and we need more mining. Low and zero CO2 technologies like electric vehicles, solar panels, wind turbines, and the infrastructure needed with all of these low and zero CO2 energy and transport technologies are mineral and metal intensive. To hit carbon dioxide emissions targets, to reduce the impact of anthropogenic emissions, and to reduce anthropogenic emissions of carbon dioxide and other harmful gases, full stop, we need more metals. We need more mining to occur. Demand for metals is likely to increase as we move towards lower and zero CO2 technology and transport, energy generation, energy storage, and transmission. Simply put, if we don't mine more, we can't reduce anthropogenic carbon dioxide emissions unless we have a real change about how we operate as a society. And I'm not just talking increased efficiency, I'm talking essentially removing large aspects of what we consider to be crucial parts of modern life. So the challenge you guys are going to face, you as young economic geologists, as young professionals within the field of economic geology, who can not only shape the Society of Economic Geologists, but also who can and will determine the way the mining industry operates. It's how we meet this increased demand for minerals and metals, but also ensure that we don't cause environmental, social, and other problems while meeting this increased demand. It's going to be a very fine balance to tread. How do we mine more? How do we extract more minerals and metals without having, significant impacts on the environment and on the social side of things? It might seem like a tall order, but these challenges are also opportunities. You'll all have the chance to make people more aware of the importance of economic geology and the minerals industry, full stop. To ensure we use minerals and metal resources in a sustainable way as possible, to ensure we practice good resource stewardship, to create value from waste. Essentially, the waste products of the last 100 or plus years of mining are sitting there waiting as resources. Resources from the metals, those, that mining waste was originally produced as a byproduct of, or for other metals that we didn't use, say, 100 years ago when these mining wastes were first generated on a large scale. Things like the critical metals, the rare earths of this world, and so on, that we are increasing in demand because of low and zero CO2 technology and so and the like. We also, we need to, as economic geologists, be involved in conversations about leaving areas we work in as close to the way they were before mining began, basically leaving them in the same state that they were originally, or as close as possible. And we need to realize the most of what we mine. It's not just often about the metals we extract from a mineral deposit, but also the waste. How can we use that waste, for example, if we're mining nickel from ultramafic mine tailings, how can we enhance the CO2 sequestration potential of those ultramafic rocks that we've mined as a byproduct of nickel extraction? Equally importantly, we need to listen and engage to people. The kind of the social challenges the mining industry is facing into social opportunities. How do we, make mining socially beneficial? How do we do this and have conversations in an open and honest way? These are things that all the mining industry is traditionally being accused of not doing. How do we flip that around and ensure we do that in all ways possible? If we don't do this, mining is going to face a bleak future. Environmental and social challenges are already delaying and potentially preventing the extractions of minerals and metals. But how do we turn these challenges into opportunities? And this is something that us as a Society of Economic Geologists and us as a broader science of economic geology need to think about. And this is something that you all as young members of this group of scientists and of the minerals industry, you all have a say, and you should all have more of a say going forward in terms of what the mining industry and minerals industry should look like in the future. You have a voice. Make sure you use it. Make sure your voice is heard as much as possible. And that's one of the things that we're trying to do within the society, is to make sure that students and early career professionals actually have voices within the society that are heard. The challenges we face, therefore, are certainly not just technical, but they're environmental and social. And as the future of our society and our science, I have faith that we can take these challenges on, not just people at the top, but all of us within our subdiscipline of the earth sciences, including the people presenting this conference, the people listening into this talk, the younger members of the community of economic geology, who essentially represent the future of our science. You're going to see some of this in the challenges and some of the challenges we face and some of the opportunities within the presentations that are actually going to take place in the symposium. So as I say, just to wrap up, the younger members of our science, the younger members of our society, you're the future of both. You're the future of economic geology, you're the future of the SEG. You have the opportunity to help shape where we go from here, what we should do, and the future of our industry, our science, and how the minerals industry is viewed by the rest of the world. Well, not just viewed, but how we act and engage with the rest of the world. These are all challenges, but as I mentioned a few times, they're all opportunities. And that's one of the most exciting things about economic geology right now. We're on the crux of this large increase, predicted increase in metal and mineral demand. How we meet that and how we ensure that the mining industry, the minerals industry, does its, effectively and operates with enhanced resource stewardship is something we need to all think about as we go forward. And it's something you increasingly will have a voice in as we move into this kind of potentially new era for mining. To sum up, you as younger members of our science, younger members of our discipline, younger members of the SEG, if not now, then hopefully soon when you sign that membership form, you're all the future. And although this may be daunting, you're not alone in all of this. You have voices, you can make them be heard, you can engage with people on all levels, and I'm sure we're going to be in safe hands with you moving into the future. There's a lot of challenges, but those challenges in essence represent great opportunities for the minerals industry to go from what might have been considered as a dirty and dark past into a bright future powered by low and zero CO2 energy and transport and the like. Thank you.
Helen, we can't hear you on mute. Please unmute your mic.
I'm clearly being a bit of a technophobe today. Okay, our thanks go to Simon for preparing that talk for us. And I hope you are all feeling inspired by it. We've just ended the poll to see where you're all from. And I see we have a mix of people from Europe and North America. And we've also still got some people from Africa spending their evening with us as well. So thanks to you all, and maybe someone at a research center in Antarctica. We'll see. Okay, so now we're going to move on to the first of our 3 technical talks from student members of the University of Barcelona and the University of British Columbia. Please submit questions for the speakers in the chat box, and then we'll get to them in the Q&A session after those 3 videos talks.
So welcome everybody to our presentation. My name is Marina Cazorla Martinez, and I finished my bachelor's thesis and my bachelor's degree 2 years ago in the University of Barcelona. And I am currently doing my master's degree in the University of Geneva in the orientation of geochemistry, alpine tectonics, and ore deposits.
And I'm Laura Gemri Hernandez. I also finished my bachelor's degree in the University of Barcelona 2 years ago. And this last year, I finished my master's degree in mineral resources, also in the University of Barcelona.
So we are both part of the Barcelona SEG Student Chapter. And before starting our presentation, we would like to thank the SEG and all the organizers of this symposium for giving us the opportunity of sharing our studies and our projects. And we would also like to thank Dr. Joan Carlos Megarejo Drape and Dr. Lizard Turroyabat, which were our supervisors of our bachelor's thesis and also the supervisors of my colleague Laura master's thesis. So yeah, during this presentation today, we will talk to you about the resources of critical elements in Bolivian tin belt deposits. This is going to be the outline of the presentation. First of all, we will introduce to you the main critical elements studied and discussed in this presentation, then the area of study, and finally the main objectives of the project. And then we will start reviewing some of the studies from this project. The first one is going to be focused on sulfides and sulfosalts based in the Animas Chocayasi Tesuyos district.
And the second one will be focused on oxides on a larger regional scale. We will then together make some final remarks and conclude our presentation.
So to start with the introduction, the main critical materials studied and discussed in this presentation are indium, germanium, and gallium, and also niobium and tantalum. And as we can see in this graph to the left, prepared by the European Commission this year, where we have some materials plotted in this graph at this economic importance versus supply risk. And we have they have determined two different thresholds. And all these materials that plot above these two thresholds are considered critical for the development of the European society. So as we can see, here is gallium, here is tantalum, here indium, here germanium, and here niobium. So they all plot above these two thresholds, so they are considered critical. And some of the main uses of these elements are, for example, for batteries, for touch screens also, and also for the manufacturing of solar panels and also electric cars.
So our area of study is the Bolivian Tin Belt, which is located in the Bolivian Andes in southwest Bolivia. This area presents a marked morphotectonic partition that reflects differences in geological history, paleostructural domains, and in the current crustal structure. These domains are from west to east, the Western Cordillera, the Altiplano, and the Eastern Cordillera. The Bolivian Tin Belt is here in red, a metallogenitic province located in the Eastern Cordillera, and its tin, tungsten, silver, and base metal deposits are world-renowned and the focus of our studies. This area is mostly composed of late Miocene to recent and intermediate felsic igneous rocks that intrude in and extruded over Jurassic and Cretaceous sedimentary and volcanic rocks. The studied deposits belong to the epithermal and xenothermal environment. So what does xenothermal environment mean? This environment is characterized by polymetallic high temperature vein deposits, with high temperature meaning between 300 and 500 degrees Celsius. These vein type deposits are emplaced in the sub-epithermal environment. So in 2019, the Bolivian Tin Belt accounted for about 6% of the global tin production, in addition to silver and tungsten. And it is estimated to contain more than 8% of the world's tin resources.
So regarding the main objectives of our project, so as I said before, this is a big project that englobes different minor studies. So this project started with the main objective of seeking a better understanding of the parameters that control these high-tech element contents and enrichment in the Bolivian tin deposits. And we wanted also to know get to know some of the geochemical tools for their exploration. So some of the specific objectives of the project include, for example, determining trace element content, such as the ones that I showed you in the first slide, in sulfides, sulfosalts, and oxides. And once we have determined this content, we can then identify which mineral phases concentrate preferentially these critical elements. Then we also want to understand the spatial distribution of trace elements along single deposits, and if possible, in a regional scale. And then we want to understand the timing of trace element enrichment along the paragenetic sequence. So if this enrichment occurs in the early paragenetic sequence or in the late stages. We also want to determine the physical chemical conditions that are favorable for the transport and deposition of high-tech metals. So if there's like a specific mechanism for the enrichment of these mineral phases in these critical elements. And finally, we want to know if these analyzed trace element contents are found in economically important values in Bolivian tin belt deposits. So now I'm going to start to review this first study from this project. So this is based in the Animas Chocallas Itesuyos district, and it's mainly focused in sulfides and sulfosalts that are indium rich. So regarding the geological setting, it is geological and geographical setting. It is located pretty close to the triple joint between the Eastern Cordillera, the Western Cordillera, and the Altiplano of the Andes. And it's also located within the Bolivian tin belt that my colleague just explained to you. And now if we take a closer look to the study area, here in the right image, we have a more detailed geologic map of the district. And as we can see, it's mainly composed by rocks that are part of a volcanic caldera complex, which are hosted by Oligocene, Miocene sandstones and tuffs, and also Ordovician sandstones and slates, which are these pink and brown. So the volcanic rocks would be these colors here. And here in this image, we can see all the different samples that have been collected throughout the different field campaigns that have been done to this mine in our project. So as we can see, these are distributed all along the surface of the district, but also in depth, so that we can have a better understanding of the distribution of the elements, critical elements in the surface, but also in the depth. So just to make clear, this district is divided in 3 different mines. So the first one is the Chocaya mine. Then we have the Animas mine, and then we have the Sitesuyos mine towards the north. And regarding the petrological study, the 3 different mines, they have more or less a very similar mineralogy, but they have some minor differences. So, for example, in the Sitesuyos mine, the sphalerite contains in some places some chalcopyrite blebs, which has been determined as chalcopyrite disease. And we can also observe that the sphalerite is banded in some places, and it's cut by stannite. And regarding the Animas mine, the stannite content is much higher, and we can also observe a huge variety of sulfur salts, such as the ones we can observe in this image, for example, Jamesonite or andorite or meargyrite. And regarding the Chocaya mine, so this one is simpler than the mineralogy of the Animas and the Sitesuyos mine, as far as we have seen. So it's mainly composed by a pyrite marcasite assemblage, which contains some small pyrrhotite grains that we will refer to as pyrrhotite remnants. And we can also observe some veins that crosscut this assemblage of pyrite and marcasite, composed by sphalerite and galena. Regarding the ore mineral geochemistry, so we did electron-proof microanalysis in the grains of the samples that we collected. So some of these microanalyses were performed in sphalerite grains, and we obtained values of indium up to 9.66 weight % in the Sitesuyos mine. And we could also observe a very high value of indium in stannite, but in the Animas mine, which is up to 4.11 weight %. And we could also observe some other indium-bearing mineral phases in the Animas Chocaya Sitesuyos district, such as rhamdorite or wurtzite. But these contents were not as high as the ones found in sphalerite and stannite. Now, regarding the incorporation of indium in sphalerite and stannite structure. So as we can see in this graph in the left, it's for sphalerite. So here we plotted all the electron-proof microanalysis that we performed in sphalerite grains in this copper versus indium diagram. So as we can see, they all plot or within this line that it's copper indium 1 or above this line. So basically what we concluded with this graph is that we need copper in the environment in order to incorporate indium in the sphalerite structure. So this could also be observed in this SEM-EDS qualitative X-ray images. So these bands that are indium rich and also copper rich, which are the lighter bands, are also depleted, so impoverished in zinc. So we could say that we have a couple substitution between zinc substituted by copper plus indium. And then regarding stannite, we could observe a correlation between copper and indium and tin and indium. So we could conclude that indium enters in the stannite structure, replacing the positions of copper and tin. And regarding the spatial distribution of indium in this deposit, we could see that in the case of sphalerite, towards the inner parts of the deposit, we have a higher content. And when we go towards the outer parts of the deposit, this indium content tends to decrease. And the same was observed for stanite grains. And in depth, we could also observe some trends. So in some of the veins studied, for example, the Animas vein, we could observe that towards the deeper levels, we have an increase in the indium content, in the average indium content. The same for the Arturo vein and also for the Chorro vein. And finally, regarding the paragenetic sequence and the evolution of the fluids, we could distinguish, thanks to the petrological study and the electron-proof microanalysis, that there were three different stages. A first one that it's low sulfidation, and a second and a third one that it's intermediate sulfidation. So we can see that there's a shift from low sulfidation to intermediate sulfidation. So some characteristics of the low sulfidation assemblage, for example, are these pyrrhotite remnants that I showed to you in the Chocaya mine. And we could also observe iron-rich sphalerite, whereas in the intermediate sulfidation stages, we could observe iron-poor sphalerite, which is typical for the intermediate sulfidation assemblages. And how is this related with the indium enrichment? So we could see that the sphalerite in the intermediate sulfidation stage, it's much higher, so much more enriched in indium than the sphalerite from the low sulfidation stage. So this was all for the Animas Chocaya acid Suyos district, and now my colleague is going to continue with the second study.
So our latest study was focused on cassiterite, as it is one of the major components of the Bolivian tin belt. Cassiterite, due to its structure, can incorporate a wealth of elements in minor and trace concentration in substitution of tin. So some of these elements, as stated before, are considered high-tech metals critical to global economy. And this would be like indium, germanium, gallium, niobium, and tantalum. And since cassiterite can form in a broad range of pressure, temperature, and composition conditions, and has a high physical and chemical resistance, it can be useful as a petrogenetic indicator. And also, due to its ability to incorporate elements such as uranium and lead, and its high closure temperature, it can be used for dating. So in this study, we determined the geochemical composition and uranium-lead ages via laser ablation ICP-MS of cassiterite samples belonging to 9 deposits from the Bolivian tin belt. The studied deposits represent different ages, depths of mineralizations, and proximity to intrusive ore bodies. So the shallower deposits would be represented by Poopo, Polquechaca, and Animas, and would belong to the epithermal environment, whilst the deposits of Kluane, Biloco, Oruro, which would be the San Jose and Itos mines, and Yayagua, Guanuni, and Boriwari would belong to the xenothermal environment. We determined that the mineralization occurred in 2 distinctive stages. In the northernmost part of the Bolivian tin belt, represented by the Kluane deposit, mineralization occurred during a rifting episode about 240 to 220 million years ago. And in the southern part, represented by the deposits of Biloco, Guanuni, and Yayagua, mineralization occurred during a major episode of basaltic magmatism about 24 million years ago. So even though the mineralization occurred in 2 different stages, spaced out in time, the composition of studied cassiterite samples is relatively homogeneous, as cassiterite is tin oxide. The composition of tin is mostly around 97 to 99% in weight. Cassiterite from the Bolivian tin belt is also enriched in iron within some deposits, such as in the Oruro area. It can reach up to 2.32% in weight. Some deposits of the Bolivian tin belt are also enriched in titanium, such as the deposit of Kluane, and in other deposits, such as in Biloko and Wononi, there can also be found an enrichment in niobium. In regards to trace element concentration, we can also see two distinctive trends. One of depletion towards the south in elements such as titanium, vanadium, chrome, niobium, and tantalum, and on the contrary, one of enrichment towards the south in elements such as indium, gallium, germanium, and arsenic. Some nuances in trace element contents of deposits and mineralization emplaced at different levels allow for the identification of some compositional trends. So deposits formed adjacent to causative intrusive complexes, such as the deposit of Kluane, Biloko, and Leliagua, are typically enriched in niobium and tantalum relative to shallower deposits and the epithermal and xenothermal environment. In addition, there are two ratios which can give us information about the proximity to hydrothermal centers, which would be the titanium-zirconium ratio and the titanium-scandium ratio, because we can see that the deposits more close to these higher temperature areas are enriched in these ratios, and these ratios decrease towards the outermost deposits. We can also see there's an enrichment of iron towards the shallower deposits. And finally, as for the concentration of critical elements, we can see that the concentrations of niobium and tantalum can reach about 1,000 to 2,000 ppm in niobium from the Kluane and Biloko deposits, and the concentrations of tantalum can reach about 114 ppm of tantalum. But when we compare these contents to cassiterite from magmatic environments and other sources, they are not as high. So therefore, cassiterite from Bolivian tin belt would not be likely a good resource of these metals. This would also be the case for germanium, since its concentrations in the studied samples are systematically very low and always below 10 ppm. This would, on the contrary, not be the case for gallium or indium. So the gallium concentrations can reach up to 7,400 ppm in the Animas-Chocaya-Sitesios district and about 1,300 ppm in Oruro. These concentrations are consistent and often higher than concentrations reported in some bibliographic studies. And this would also be the case for indium, which can reach concentrations above 1,000 ppm in Oruro, Wari-Wari, and Animas-Chocaya-Sitesios, with the highest concentrations that were found in Oruro from 1,300 ppm. However, the concentration of these elements in cassiterite is not as big as in sulfides, which we will now discuss.
So now the final remarks of the two studies that we have just reviewed. Laura, if you want to start.
Yes. So when we talk about critical element content, we have seen that sphalerite and stannite are usually present higher concentrations of these critical elements when compared to cassiterite. But in the case for cassiterite, the concentrations of indium are much higher than the concentrations of gallium, and these ones are higher than niobium, tantalum, and germanium, which would be relatively small.
And regarding the indium enrichment in some of these spaces, so for example, in sphalerite, as we could see before, this enrichment is correlated with the copper content. So we could conclude that when we have a sphalerite that is rich in copper, it could be also possible that it's also enriched in indium.
For cassiterite, the concentration of indium generally depends only on the content of indium from the mineralizing fluid. And when we talk about spatial distribution of critical elements on the regional scale and when we talk about cassiterite, we can see that the northernmost deposits are usually enriched in niobium and tantalum, and the southernmost deposits would be enriched in indium and gallium.
And regarding district scale, so smaller scale, we can see that there's an enrichment of these elements towards the inner parts of the deposit, in the case of Animas Chocayacitesuyos, for example, and towards the outer parts, we have a decrease in the content of some of these critical elements. And we could also observe this in depth. So towards deeper levels, we can observe that we have a higher indium content. And regarding temporal distribution of critical elements, so at least, well, yeah, in most of the deposits in the Bolivian tin belt, we can observe a shift from low sulfidation to intermediate sulfidation throughout the paragenetic sequence of the deposits. In the case of Animas Chocayacitesuyos district, we have the indium enrichment in the intermediate sulfidation assemblages. So this is not the same in other deposits. For example, in the Wari Wari deposit, which was the one that my colleague Laura studied for her bachelor's thesis, where she could observe that the enrichment of indium takes place in the low sulfidation assemblage, so in the iron-rich sphalerite. And finally, as a last question, are these trace element contents found in the Bolivian tin belt deposits economically relevant? So for answering this question, we prepared this graph where we have the maximum contents of indium found in the studies from our project. So in orange would be the sphalerite, and on green the stannite, and on blue the cassiterite. So in the case of sphalerite and stannite, we can see that the higher contents of this critical metal are found in the Wari Wari and Animas Chocayacitesuyos mines in districts.
And for cassiterite, generally the concentration is higher also in the Wari Wari and Animas Chocayacitesuyos mines, but in the area of Oruro, so in the San Jose and Itos mines, there's also a high concentration of indium in cassiterite, which it would be interesting to look at the sulfides in this area because they may also be enriched in indium.
Yeah, so something we want to point out is that to get to know if these critical elements amounts found in these deposits are economically profitable, we need to combine these geochemical studies that we have performed with further metallurgic and mining focused studies that we hope to be able to perform in our project in the future. So this was all for today. Thank you very much for your attention. We hope you enjoyed the presentation. And yeah, this was a very nice moment, very funny moment in one of our field campaigns that we did in Bolivia for sampling some of the deposits that we were going to study. So yeah, we have here the llama and we are scared, but but it was a funny moment anyway. So thank you very much for your attention, and yeah, once again, we hope you enjoyed it.
And enjoy the rest of the presentations.
Yeah, of course. Bye bye, and thank you again. Here you have the references, so the main articles that were cited in this presentation, and yeah, finally the other references that we used and cited throughout the presentation. So yeah, bye bye, and thank you so much.
Hi, my name is Katrin, and in the next 10 minutes or so, I'm going to tell you a bit about my master's research as part of the Carbon Lab at the University of British Columbia. Before starting, I would like to acknowledge that I am located at the University of British Columbia on the traditional, ancestral, and unceded lands of the Musqueam, Coassalis peoples and the Tsleil-Waututh nations. I would also like to acknowledge that the research field site of this study is on the land of the Tlaxten Nation and Pinche-Wuten First Nation. This study is on the formation and preservation of brucite and aurite in a serpentinized ophiolite, central British Columbia, and the implications for carbon sequestration and nickel recovery. The incentive of the study is to help combat the climate emergency. To be able to do that, we need to capture and store carbon dioxide from the atmosphere, as well as mine metals efficiently and environmentally to phase out fossil fuels. There are two key minerals in serpentinite that are needed to be able to do this. Brucite, along the serpentine, can be used to sequester carbon dioxide, and averroite is a potential source of nickel that can, for example, be used in electric car batteries. Here you can see two petrographic images of both of these minerals. Brucite is in this image surrounded by magnetite and serpentine, and on the right-hand side is a coarse averroite grain with some minor nickel sulfides and magnetite. Knowing both minerals' distribution, abundances, and correlation can help make carbon neutral or carbon negative mining possible. And that is through ex situ carbon mineralization. That is the idea that reactive minerals, such as brucite, in the mine tailings or the mine waste, can react with carbon dioxide to form stable carbonate minerals over geological timescales. So the field site is the Dakar area, which is located in the Cache Creek terrain, shown in yellow over here, with all the ultramafic rocks in British Columbia shown in black, and the Dakar area is in the center. The ultramafics in the Dakar area are a basal section of an ophiolite, and they're variably serpentinized and carbonate altered, shown with the different patterns of the purple area here. There's also mapped the averroite grain size and sample locations for this study. This area is the perfect place to study brucite and averroite, as they have been shown to be in high abundances in this area. So we have four main research questions that we are collecting information to be able to answer. The first one is, how does the protolith composition affect the formation and distribution of brucite and averroite? 2, what is the hydration and carbonation history recorded by these rocks? And 3, how does metasomatism or carbonate alteration affect the abundance and grain size of these minerals? And lastly, does the temperature and pressure of metamorphism dictate mineral assemblages and abundances? So during this field petrographic and geochemical study, we found the protolith of the ultramafic rocks to be mainly composed of harzburgite with lesser liersolite, dunite, and pyroxenite. In this outcrop image over here, you can see a pyroxenite dike that crosscuts dunite and harzburgite layers. On the right-hand side is a mineral normalized abundances plot of the samples with normalized to olivine, orthopyroxene, and clinopyroxene. And the different colors show the estimated olivine-pyroxene ratio of the samples. So commonly, ultramafic rocks are altered and metamorphosed via partial to full hydration. This process is referred to as serpentinization. So serpentinites are composed of serpentine mineral group, which can be lizardite, antigrite, chrysotile, or other minerals. It can also be brucite, magnetites, sulfides, alloys, and others. And because these serpentinites contain highly reactive hydrated minerals, they can be readily carbonated to form magnesite, other carbonates, talc, quartz, and minor fuchsites. This process is the natural analog to carbon mineralization. And just a note here, the two minerals that we are looking at for this study are stable in the serpentinites. These two processes can also be seen by looking at the volatile abundances and the mineral abundances. The x-axis of these two plots is the loss in ignition, so both the H2O and CO2. And you can see here that the degree of serpentinization from roughly 0 to 15 weight% LOI is the serpentinization process, while from around 15 to 40 weight% LOI, it's the carbonate alteration. And this is seen in the serpentine and brucite mostly for serpentinization, and magnesite mostly for carbonate alteration. This is useful for exploration and first estimates of the two minerals. So in more detail, is the brucite abundances plotted up on this graph over here. The x-axis is the same as in the slide before, and we have the brucite abundance on the y-axis. As you can see, the abundance of the mineral is increasing with a higher degree of serpentinization. It varies with the original olivine-pyroxene ratio of the protolith. So the higher the brucite abundances are in the higher olivine-pyroxene ratio, or in the dunites. As well, we can see the averite abundances plotted up here on the right-hand side. They also increase with a higher degree of serpentinization, but the highest abundances and the coarsest grain sizes are found in the olivine-rich harshbagites rather than in the dunites. This is because of the presence of pyroxene that helps hydrogen formation, which stabilizes averite. So we combined a variety of methods, including petrography, mineral compositions, X-ray diffraction, thermogravimetry, Raman spectroscopy, and stable isotope analyses. And we found 5 distinct alteration stages: 3 serpentinization, SERP1, SERP2, and SERP3, and 2 carbonate alteration stages, CARB1 and CARB2. These stages differ in fluid composition and pressure and temperatures. So brucite is most stable in the later part of SERP1, that is SERP1b, and averite is both in SERP1b and SERP2, but is more stable over longer periods than brucite. These 5 alteration stages are also summarized on a regional scale in this image over here. At first, in a super subduction zone, the harshbagite, dunite, and pyroxenite form in the upper mantle. Then in a continental environment, during or post terrain accretion, SERP1 and SERP2 form and are sourced by meteoric fluids. The estimated temperatures of SERP1 are roughly 250 to 300 degrees Celsius, while SERP2 is estimated to be from 324 to 450 degrees Celsius. The main reason for this is we have the presence of metamorphic olivine in SERP2. And during these 2 stages is the main brucite and averite formation. Lastly, at a later point, we are also in a continental environment where we have CARB1, SERP3, and CARB2 occurring. The carbonate alteration stages are sourced by crustal fluids. They are possibly brought up by stratigraphically lower rocks through shear zones. And these 3 stages consume brucite and averite. So in conclusion, serpentinization increases brucite and averite abundance, but carbonate alteration consumes them. The brucite abundance is primarily controlled by protolith composition, olivine-pyroxene ratio, serpentinization at low temperature in SERP1b, and the lack of metasomatism. Averite is controlled by a combination of protolith composition, olivine-rich harshbagite, serpentinization extent in SERP1b and SERP2, and low oxygen and sulfur fugacity. Here you can see an image of a hand sample where we have the disseminated averite grains and serpentine and brucite in the matrix. So thank you for listening, and feel free to reach out by email, Twitter, or LinkedIn if you have any follow-up questions or want to chat. Thank you.
Thank you. Okay. Thank you for that, Milena, Laura, and Catherine. Please could you unmute yourself and turn on your videos? We've had a few questions that have come in. Okay. So,
Hello, everybody.
hello. So, Milena, we have a question from Lingli Zhu. Okay, she said, thanks for your great talk. Do you think the spatial distribution of indium has something to do with the source rocks?
Okay, so from the results that we obtained, at least in this study from the Animas Chocayas district, we did not see a clear correlation between the lithologies, the different lithologies in the host rock and the mineralization itself. So yeah, basically I would say that it's mainly related with the composition of the mineralizing fluid rather than the host rock itself. So basically, towards the inner parts of the deposit, we have the higher enrichment in indium, and towards the outer parts, we have the lower enrichment in indium.
Okay, so she may have potentially meant the source rocks as in the intrusion that the fluids have evolved from, I guess.
Okay, so source rocks, not host rocks.
Yes.
Okay, so yeah, that's something that we should study in the future. So possibly like doing isotopes or something like that to get to know like the source of these fluids, and yeah, probably the source has definitely a role in this indium enrichment, of course.
That's great, thank you. And to yourself and Laura, we have a message from Marie. She says, thank you for your nice presentation. Since it was briefly mentioned, do you know what the scandium concentration was in your deposit or minerals?
Yes, thank you. In my case, in our case, we only studied the concentration of scandium and cassiterite. So the global concentration, if we take into account all the Bolivian Tyndall samples we analyzed, reaches about a maximum of 870 ppm more or less, with an IQR of 55 to 2 point something, like really, really small. And the highest concentrations were found in the Wanuni deposit and the lowest in Animas Chocaya Suyos, but the values for Colquechaca and Popo are also low, with maximum amounts of scandium below 50 ppm. The other deposits tend to range between these values. But yeah, the highest concentrations were found in the Wanuni deposit, about 870 ppm.
Okay, thank you very much. And feel free for everyone to continue your conversations in the chats if there are any follow-up questions. Katrin, thank you very much for your presentation. That was wonderful. I wondered if you wanted to speak more to explain the benefits of carbon sequestration and how kind of these ultramafics can be used in this way. I think a lot of us know a little bit about using volcanic ash in farming lands, but can you expand a little bit with ultramafics?
So in ultramafic rocks that host mineral deposits, it's possible to use the tailings for carbon mineralization, as the tailings are already ground up and crushed, so relatively fine-grained, depends. And then they have more surface area, and if they host these reactive minerals that are either magnesium or calcium rich, they can, via passive carbonation, they can react with the CO2 in the atmosphere. So at the surface of the mine tailings, you can form these stable carbonate minerals. There's another way that some people in my research lab group are trying. We have pilot experiments. That is, they're injecting CO2 directly from a point source into the tailings, and that can also carbonate. But this is all, the idea is that it's all at the surface.
This is different than,
yeah, that's the idea. And there's a lot of ongoing work, but deposits such as nickel, cobalt, and diamond deposits that are in ultramafic rocks are the best feasible.
Thank you very much for expanding upon that. That's great. Okay, we will now move on to our second set of talks. So you're going to hear from student members of the University of Leicester. Again, please submit your questions into the chat box and keep on talking. Thank you.
Hi, I'm Charlotte Clark. I am a fourth year applied and environmental geologist here at the University of Leicester, and today I will be discussing my research project, which is the potential for a Norilsk-style nickel-copper PG sulfide mineralization in the Kalahari zone, Botswana, in this project is with Ekandjo resources. So firstly, just a couple of aims of my project, which I'll be discussing later on. So the first aim is determining geochemical indicators of sulfide segregation and establishing any geochemical differences between different mafic suites. And my second aim is to determine which country rock played a key role in contamination and consequently sulfur saturation. So how am I going to find indicators of sulfide segregation? We do that by looking at copper-palladium ratios, and you can also use copper-zirconium ratios. And geochemical differences between mafic suites is by downhole geochemical plots. And for country rock contamination, we are going to identify the origin of xenoliths within samples and any geochemical signatures of crustal contamination. So firstly, just a bit of background on the formation of magmatic sulfide deposits. The majority of magmatic sulfide deposits are spatially related to cratonic and paleocratonic boundaries. Many are also related temporally to large igneous provinces and thus plume related. This spatial relationship is likely due to the impact of a mantle plume on the base of the thick continental lithosphere, which is then deflected to the thinner cratonic margins. At the thinner margins, decompression melting can occur. This is illustrated in part A and B from this figure from Barnes et al. 2016. The melts can then ascend through the crust by large transit lithospheric faults at the cratonic margins. Further ascension is possible through dike and silt propagation. During the magma ascension, the sulfur undersaturated magma can become contaminated with continental crust, which may allow it to become sulfur saturated if contaminated by appropriate country rocks. The most efficient way of incorporating crustal sulfur is through the direct melting and assimilation of crustal rocks. The sulfur within the magma can then scavenge the metals from the melt, where the sulfides then get segregated into an immiscible sulfide liquid. This immiscible sulfide liquid will then be transported and deposited into trap sites. A summary of the key features needed to form a magmatic sulfide deposit. So you need the assimilation of crustal sulfur. Many of these parental mafic magmas are generally sulfur undersaturated, so you need the addition of crustal sulfur to allow for the formation of metal sulfides. You then need the segregation of an immiscible sulfide liquid, which may form at deeper levels than the final deposit depth. And then you then need the transportation and trapping of an immiscible sulfide liquid, with the liquid being entrained upwards as fine droplets and mechanically deposited. However, these droplets may also be entrained upwards and then subsequently downwards with magma flow into a deposit site. The Kalahari Citrus Zone is located along the western margin of the Kapval Craton within the Kaeter Belt in Botswana. The Kaeter Belt represents an area affected by multiple orogenies, including the Kaeter and Magondi orogeny. The Kalahari Citrus Zone is proposed to mark the line of collision between these orogenies and the Kapval Craton. The intrusions which are of particular exploration interest are the post-Karoo mafic intrusions, which are believed to represent the feeder systems of the Karoo flood basalt, which has since largely been eroded. These mafic sills and dikes are intruded into a series of sedimentary supergroups, including the Transvaal supergroup, which contains a series of mudstones, sandstones, dolomites, banded iron formations, and volcanics, and the Karoo supergroup, which consists of siltstones and mudstones with some coal intervals within particular formations. So the magmatic sulfides at the Kalahari Citrus Zone are believed to be a close analogue to the world-class magmatic sulfide deposits at Norilsk. The Norilsk intrusives are located along the northwest margin of the Siberian platform and are thought to represent the feeders to the Siberian continental flood basalt. The deposits are located along the junction of two paleorifts along a regional scale fault, the Norilsk-Karolak fault, believed to be part of the magma feeding or conduit system. The Norilsk complex was emplaced within a series of sediments including Devonian sulfate-rich evaporite and middle Carboniferous upper Permian coal measures. There are many features of similarity between Norilsk and the Kalahari Citrus Zone, similar tectonic settings and and migration pathways, with both deposits are believed to be the feeder system of flood basalts, and there are similar country rock lithologies. Okay, so back to my aims. What evidence of crustal contamination do we have? Well, within the Kaeter intrusions, there's petrological evidence of crustal contamination in the form of xenoliths in chilled margins of intrusions. For this particular example on the screen, the intrusion is emplaced within the coal measures of the Karoo supergroup. And this reflected light image shows a xenolith of coal with a halo of pyrite around. Coal can act as a reductant to form sulfate into sulfide, and this represents strong evidence of local contamination. However, if we need to know more widespread crustal contamination indicators, we need to then look into the geochemistry of these intrusions. The evidence for geochemical crustal contamination is by a marked depletion in the tantalum and niobium within the incompatible element diagram. This is a trend which is very similar to the upper continental crust, which suggests widespread crustal contamination throughout all the mafic intrusions in the Kalahari suture zone. However, this does not give an indication as to which country rock played a key role in that contamination. If we're going to get an indication as to which lithology played a role, we can compare the aluminium oxide against the calcium oxide. Lithologies such as siltstones and mudstones contain aluminium, whereas carbonates contain more calcium oxide. Samples from the Kalahari suture zone show evidence of contamination from silt or mudstones. This lithology is widely available within the Kalahari suture zone from the Karoo supergroup. So what evidence do we have of sulfide segregation? Well, copper and palladium ratios have been used to provide evidence of sulfide segregation. Both copper and palladium act as incompatible elements within magmatic system, meaning that during fractional crystallization, the elements prefer to remain in the liquid rather than going into a crystal phase. Palladium has a higher partition coefficient than copper, meaning it is extracted more readily into sulfides than copper. Thus, an elevated copper-palladium ratio indicates towards sulfide segregation, as there are large concentrations of copper with a small concentration of palladium, as the palladium has already been taken in by earlier sulfides, which have since been segregated from the melt. A small ratio can indicate towards sulfide accumulation, as there will be higher concentrations of palladium due to the presence of sulfides. The copper-palladium ratios within the mafic samples in the Kaeter are slightly above mantle ratios, with particular examples having extremely elevated ratios, such as a sample in 8A which has a copper-palladium ratio as high as 784,000, compared to mantle ratios which are typically 1,000 to 10,000. So this project is still ongoing, and so this is what I will be doing next. So I'll be looking at the downhole geochemistry logs to determine any differences between different magma suites, such as possible different pulses of magma. And I will be looking at the implications for a massive sulfide within the Kalahari suture zone. So this is including a possible grade of the sulfides present and where that massive sulfide may be. So the importance of magmatic sulfide deposits for new battery technology. If we're going to take steps in lowering our carbon footprint, changes need to be made to everyday life. One of these key changes is switching to electric batteries. If we're going to meet for the demand for a more electric future, then the supply of key metals for high-tech battery production needs to be met. This figure illustrates just 3 different types of electric batteries available. The main metals within these batteries are dominated by cobalt and nickel, metals which are both available within magmatic sulfide deposits. The platinum group elements can also be used for electric batteries. The exploration for new magmatic sulfide deposits can help meet the demand for these key metals for a low carbon technology future. Thank you for listening to my talk on the potential for a Norilsk-style magmatic sulfide deposit within the Kalahari suture zone. If you have any questions, please feel free to ask them in the Q&A. Alternatively, you can email me with either of the emails on screen.
Hi everyone, My name's Molly. I'm an MGEOL student at the University of Leicester, and my current research is on the applications of deep eutectic solvents to recover gold and useful byproducts. So traditionally, gold is recovered using cyanide as the reagent. Now, there are a few environmental and social issues with using this. Firstly, the form we use it in is sodium cyanide, NaCN, which is highly toxic. Therefore, any mine tailings where cyanide has been used pose a threat to the environment, as they might contain toxic concentrations of this sodium cyanide. This then runs the risk of spilling and getting into drinking water supplies or polluting rivers and affecting wildlife. Cyanide has actually been banned in some countries such as Germany and Turkey, and also some US states such as Wisconsin and Montana. And finally, we can't recover rare and useful byproducts using cyanide, such as tellurium. So there are a few case studies worldwide of disastrous tailings collapses which have led to cyanide reaching the environment. One key example is the Baia Mare example from Romania. This is where 100 meters cubed of contaminated liquid spilled into local river systems. This contained 50 to 100 tons of cyanide. It first affected the Somme River, but once it's in the system, it obviously travels. So an isolated spill can have a really long-term effect and large-scale environmental impacts. The spill then affected rivers such as the Tisza and the Danube, and the contamination eventually travelled into the Black Sea. There was an increase in wildlife mortality following this spill, killing thousands of fish, including 20 some protected species. This photo is an example of some of the disastrous after effects. It also poisoned drinking supplies for many local people. So naturally, because of these disasters, the public's perception of cyanide is very poor. While industry cyanide usage is actually typically dealt with very safely, spills such as the Baia Mare mean that a large proportion of the public will be very wary of cyanide, therefore they won't be happy with cyanide operations occurring near them. There was actually a case in Australia where the pushback from the public was so significant that the mining company were driven to cancel their proposal for using this reagent in one of their mines. This was because there was an 85% objection from the public about the use of cyanide and the potential for contaminated tailings reaching their water system. This picture here is from Romania following the disastrous spill, and it shows there's a really low public acceptability there. So this is something that modern mining companies really need to consider when deciding what reagent to use in their operations. So taking all of this into account, there seems to be a real need for a viable alternative to cyanide. One such alternative is deep eutectic solvents, or DES. These have been developed at the University of Leicester, and they are ionic compounds of anhydrous salts, which are liquid at low temperatures. They also boast being environmentally benign and chemically stable, and at low temperatures they can dissolve gold from ore, which can then be recovered by electrolysis. Another advantage is that they have a low vapor pressure, so they don't smell or release any gases, and they're mixed and made from non-toxic, fairly environmentally benign ingredients. Another huge advantage is that they can recover the rare resource tellurium, which is typically a byproduct of the gold processing industry. So now we need to consider how successful are these solvents and reagents, and how do they compare to cyanide? There have been numerous studies from the University of Leicester which suggest a high level of success at extracting gold, silver, and telluride minerals from ores. Additionally, the reagent is effective at low temperatures of 45 to 50 degrees, therefore requiring little energy to operate really efficiently, improving the green credentials of this method. Leaching rates using the reagent have generally proven to be really fast. For example, electrum dissolves up to 40 times faster by DES compared to cyanide. Although the dissolution rate does depend on several other factors such as mineralogy, degree of liberation, etc. A really significant benefit of utilising DES is its ability to selectively dissolve various minerals. For example, tellurides and electrum can be dissolved through an oxidative leach. However, sulfides can be selectively dissolved in a deep eutectic solvent by electrolysis. So finally, I'll just touch on what these deep eutectic solvents are actually made of. So they're eutectic mixtures, which means the mixture has a lower melting point than the individual components of ammonium salts like choline chloride, as well as urea, which acts as a hydrogen bond donor. One huge benefit is that these components are readily available, as they're already produced in really large quantities. For example, choline chloride is actually produced as a B12 food additive on a megaton scale, and urea is produced as a common fertilizer around the world. These are both relatively cheap components and are relatively non-toxic, biodegradable substances which can be easily and safely disposed of and recycled. So now I'd like to touch a little on the energy problem and why the recovery of the rare resource tellurium is really important to present society. As we're all very aware, global warming is a real crisis, and as part of decarbonising our future, we must find alternative sources of energy to power our lives and make these actually our primary sources of energy. One source of green energy is exploiting solar energy from the sun by using solar panels. However, in order to move from the traditional fossil fuel sources, there are some materials which we must mine in order to operate the renewable resources. One of those is tellurium, a rare mineral that contributes as an essential component to building photovoltaic solar cells. And the global demand for this rare material has surged in the last decade due to continued efforts to increase this proportion of energy that we're producing worldwide from renewable resources rather than coal, oil and gas. UN agreements such as the Paris Agreement means the demand for this resource is predicted to continue to increase over the next 10 to 15 years. This chart is really here just to show how much the global demand for solar energy has increased and how it shows no signs of slowing down. We can see from 2000 to 2019, the use of solar panel has absolutely skyrocketed, and in order to continue to grow this aspect, we must continue to find and mine these raw materials that are absolutely necessary. And presently, the tellurium demand is met by recovery during copper processing at large high-grade copper deposits like porphyry deposits. However, these deposits are becoming rarer and rarer to discover, and it's becoming less economical to recover the tellurium from these. Therefore, in order to meet the demand, we must find alternative sources of tellurium. And many gold deposits actually have really high tellurium grades, especially those which are epithermal. Now for my research specifically. I'm assessing the success of deep eutectic solvents in the Gold Hill project in Colorado. The Gold Hill project encompasses a few different small-scale inactive mining operations in Gold Hill and Boulder County silver and telluride mining district. This here is a photo of the small town Gold Hill, and mining here actually began with the discovery of placer gold around 160 years ago, and the pinnacle of mining was in the late 1900s. It's estimated that since this time, Boulder County has produced over 1 million ounces of gold, and the majority of this has been sourced from the Gold Hill district, and a great proportion of which is included within this Gold Hill project. So what we're looking to do for this company is prove that deep eutectic solvents can recover a large proportion of these gold and silver telluride minerals from the site. This adds both financial and environmental credentials to the company by recovering the useful tellurium, which would typically be a byproduct. Although I'm yet to complete the leaching experiment, I've gathered some data which can really help predict the success that the DES may have. SEM EDX results and thin section studies have informed mineralogy, some of which is the gold telluride mineral Kalahari as shown here. It can also inform textures and allow us to make predictions. I'm interested in everything that you typically are for processing, so the more liberated and exposed the target minerals are, the more likely we are to successfully recover and leach these. And it's important to know what our target minerals are associated with and where the gold, the silver and tellurium is held the most. This work has been really difficult to conduct remotely this year. However, the University of Leicester have really worked with the students so we can still make our projects as great as possible. Here's a photo of me working from home with my transmitted and reflected light microscope delivered by the excellent University of Leicester technical team. So, what is the future of gold processing? Well, I think it's really clear that we need to find an alternative to cyanide. One which is not only more environmentally friendly and has a better public opinion, but that can also recover all of that valuable material and all those necessary resources for us to move forward in the future and develop renewable energy. I think deep eutectic solvents have the potential to solve both of these issues as an environmentally benign, chemically stable reagent which can recover tellurium. If you've got any questions about my talk, feel free to ask me in the Q&A session or email me. My information is on the screen now and I'll try my best to answer. I hope you've learned a little something about tellurium and deep eutectic solvents. Thank you.
Okay. Thank you for that, Charlotte and Molly. I've got a question for Molly, first of all. Do you know if deep eutectic solvents are used anywhere at the moment? And maybe how likely they are to kind of start being used?
Yeah, hiya. At the moment, they've only been used in testing for this application anyway. So the actual large-scale industrial uses of them haven't been figured out yet. But it's looking really promising from the small-scale experiments we've been doing.
Okay, that's great. So you're not yet kind of there on the economics of kind of scaling it up yet?
Yeah, that hasn't been completed yet, unfortunately. But I think it could happen.
That's great. Well, that was a really lovely talk. Thank you so much for sharing that with us. Is Charlotte there?
Yeah, hi.
Hi, thanks for your talk. That was lovely. I wanted to ask, so our earlier talk from Elena and Laura talked a lot about the trace elements in the tin and cassiterite deposits. And I wanted, well, tin deposits. I wondered what trace elements you have seen in your deposit, in your study area, and what you think about the potential of recovering trace elements as in byproducts.
I haven't really been looking at much trace element spherics. It's still in the quite early stages of just trying to find that nickel and copper mineralization. So I'm not really sure on the any trace elements in it because sulfides that are present are extremely small and in low concentrations anyway. So if I'm honest, I'm not quite sure about any trace elements that are of any economic worth yet at the Kalahari yet.
Okay, well, thank you very much, both of you, for submitting your talk and getting involved in it. We're very, very thankful for you. We're going to move on now, and if anyone has any further questions, please just drop them in the chat. Okay, so that wraps up part one. And before moving on to the panel discussion, we'd like to share a video collage of all our contributors' perspectives on the role of economic geology and geologists to meet the challenges of the future.
I want to become an economic geologist because I believe we are absolutely essential in order for the world as a whole to move towards a more sustainable way of living.
Geology is really pretty much where all of our natural resources are coming from.
The path to sustainable development is lined with minerals.
Lately, new technologies like solar panels, electric vehicles, communications need a lot of elements that we are not used years ago, like gallium, germanium, niobium, tantalum, rare earth elements.
Elements like lithium, copper, cobalt, and zinc are vital for the development of environment-friendly technology, and they can only be obtained through mining and exploration of new ore deposits.
I am really interested in economic geology because I think it's key for the development of countries.
Economic geology is actually the branch of geology that considers a lot of factors in terms of removing minerals from the ground. So you would look at your environmental, your political, your economic, and your social factors and consider whether removing that material is actually worthwhile.
Of course, it also helps with the development of the areas around the mines and also the taxes that go back to the government so they can invest to solve other issues.
Locating and extracting geological resources are vital to tax revenues and economic growth.
Very important it is for us as geoscientists to contribute to their discovery and their recovery in the most responsible way and sustainable way that is possible.
Whether this is finding greener methods of extraction or reducing the chemical footprint that the mining industry has.
We need to be able to extract these metals in a green and non-invasive way to no longer scar the earth.
And mining companies are becoming a lot more socially responsible, but I would like to continue pushing that responsibility and ensuring that wherever we mine, the people who live there and live near there are really well looked after, and that they benefit from the mine just as much as the world does from extracting those metals and materials.
In countries like Germany, you have very advanced mine reclamation systems, and that's something I want to implement in my country. This shouldn't just be done after. This is something that should be implemented before a mine is even constructed, so that land is assured, it's assured to succeed or thrive after people are done mining in that area.
Economic geologists should make their due contribution for this.
We as economic geologists will need to be up to the task to basically extract and produce metal in a more sustainable way.
We need to make sure that we are helping people understand not only where, but how we extract the metals that they use every single day in their routine lives. So there's an opportunity for us to maybe go back to a school or a university and give a talk, giving our experiences of what the industry is actually like, or even just having conversations with family and friends.
As an industry, we need to continue to improve safety for our people. And we need to become increasingly socially and environmentally responsible.
As a field geologist, perhaps we will be the first one into a new project or into a territory, and we will need to be aware about the principles and guidelines for protecting the environment, for early community engagement, and at the same time working responsible in a safer way than before.
Now, geological knowledge itself is quite important, and it's not only important in the extraction, but it has multiple end uses as well. Land use planning, environmental monitoring, water abstraction, and construction are just some of the many uses.
This means it's a very important time for us geologists to share our knowledge and participate in the decisions being made about our resources and any other possible uses of the subsurface to tackle the big environmental challenges that we're currently facing.
And I believe that through innovation, through new ideas and new technologies and new processes, we can go a long way to improving and optimizing our industry. But this all requires diverse teams of really skilled and intelligent and really open-minded people.
If you ask me, I see our generation of early career professionals and students are well up to the challenge. In fact, I dare to say that we're motivated by this challenge.
And so for me, there cannot be truly any sustainable development without geology and geological knowledge.
Right, we are now going to move on to the panel session to discuss the challenges that the mining community needs to overcome and the support through training and mentoring that the future geologists will need to help kind of tackle this problem. The panel will be moderated by Lauren Zeek, a PhD student at the Colorado School of Mines. And I will hand over to her, and hopefully the panelists will all pop their videos on and unmute themselves.
Thank you, Helen, and thank you to the NUI SEG Student Chapter. I'll wait for everybody to get their videos. Great. Our panel today is going to focus on sustainability, social responsibility, public perception, and career advice. I'd first like all our panelists to briefly introduce themselves, starting with Sarah.
Hi, Lauren. Thanks for the introduction. So yeah, I'm really happy to be here. I started out as a geologist many years ago now, actually University of Leicester, so it's great to see people from the university here today. And yeah, I was motivated to study geology. I loved the kind of big picture thinking, solving these complicated problems in 3 dimensions across space and time and everything else. So I went off into industry, worked primarily as a mineral exploration geologist for around 6 years. Got experience with the Geological Survey on the Tellus project in Northern Ireland. And then I went into private sector. So working for a lot of junior mining companies, primarily in Ethiopia and then back in Ireland as well. And it was really during my time in Ethiopia that I got so curious and excited and passionate about this huge opportunity for us as geologists to contribute to sustainable development. So as many of you have mentioned, geoscience basically underpins everything that we do as a society, and it's becoming more and more critical that we as geologists or geoscientists have a voice at the table, and that we are actively contributing and participating in this resourcing future generations challenge. And so when I was in Ethiopia, yeah, that really sparked my passion, being right in at the interface between investors, junior mining companies, governments, communities, artisanal mining. It was just so fascinating for me. So I stepped out. Actually, I've taken a bit of a detour. I went to business school and studied innovation entrepreneurship. And then I've also picked up a few different pieces of the puzzle from international development, responsible investing, and now I'm working with deep science and technology startups, trying to unlock the trajectory of those to have a climate impact across resources. So I'll pause there.
Thank you. Subaru, how about you next?
So hi everyone. So my name is Subaru Tsuruoka. So I'm currently postdoctoral research fellow at ICRAC University College Dublin. So yeah, so I went to Coral School of Mines for my PhD. And after that, so I worked in industry for 2 years. Yeah, then so yeah, I came to Ireland so for my postdoctoral research. So I'm currently working on Central African Kappa Belt. Yeah.
Thanks, Subaru. Fabian, how about you?
Hi everyone, so I'm Fabien Rabérard. So I'm originally from France, but I've been based in Vancouver in Canada for the past 7 years. I've got background in industry with junior and major mineral exploration companies, but also research and innovation with a startup company. I'm currently a project geologist at Equity Exploration, working on the planning and execution of exploration project in British Columbia. So I'm also the chair of the SEG Early Career Professionals Committee, which aims to guide you students and recent graduate people to make a smooth transition to the mining world through education and training activities. And I'm just taking this opportunity at the very beginning to thank all the organizers for putting this event together and inviting me. And thank you everyone for joining. I hope you're going to enjoy it. Thank you.
Thanks very much, Fabian. Karina, you next, please.
Hi, everyone. Good morning, good afternoon, good evening to everyone. I'm Karina Ndauriwa, a mineral exploration geologist with Gecko Exploration in Namibia. I started my early career in the Geological Survey of Namibia in the Division of Engineering and Environmental Geology. I worked there for about 4 years. And then I moved to the to an exploration company working in the Kluane region of Namibia, where I still currently am since 2012, working on a variety of projects there.
Awesome. All right, so as we go along, I'd like to encourage audience members to submit questions in the chat. I'll direct my questions to one panelist at first, but any other panelist should feel free to jump in. And starting things off, Sarah, I'd like to ask you about sustainability. What does sustainable development mean to you with respect to mining and specifically social licensing, and what are some ways we can achieve this?
That's a great question. So yeah, sustainable development basically is finding a way to meet our society's needs without compromising our future, essentially. And so I think a large part of it is finding better ways to do business, leveraging technology, but also understanding that society is driving demand, and if we don't also consider consumption and the way that we do business, so we have this kind of linear economic model, that's a huge part of the conversation that I think we're seeing people more and more recognize around the social license aspect. Yeah, I find this really fascinating. So actually I studied this when I went to business school. I did a deep dive on this around the cost of conflict for the mining industry and what we can do better to try and coexist with communities, and specifically artisanal and small-scale mining communities. So it's no longer enough for us to find economically viable deposits. We have to really take into account every single aspect of the environment in which we're operating. And so I think it really shows that, yeah, it's no longer business as usual. We really have to promote innovation, both business model innovation and technological innovation, to find ways to resource future generations while ensuring that we're having a sustainable impact as far as possible that we can. So there's so many different things like emerging, like urban mining and circular economy models, and coexistence between large and small mining. And I think what I find exciting too are all the different pressures around the topic. So if you look at what governments are doing around empowering small mining and encouraging that, looking at more sort of modular automated mining, like how we use robotics and AI, looking at what investors are demanding of the mining industry. So even now we're seeing like tech giants starting to invest into mining because they know they need the lithium and the cobalt and everything else to actually produce their products. And then, yeah, business model innovation. So companies looking to vertically integrate with mines, like we've all seen things that Tesla has said. And I think, yeah, it's an exciting time to be a geoscientist because things are changing so fast, even in the last 5-10 years.
Absolutely. Thank you so much. Those were really great points. And Adriana, next question. Did I not allow you to introduce yourself? I'm so sorry.
No, I didn't.
Don't worry. The next question to you.
Okay, well, then I will introduce myself first. Well, my name is Adriana Guatame Garcia. I'm originally from Colombia, but I'm now based in the Netherlands. I did my undergrad in geology in Colombia, and then I worked for over a year, almost 2 years, in the Geological Survey over there. And then I moved to the Netherlands, where I did my master's in mineral exploration. And later, stayed here in the Netherlands, but different university for my PhD, where I also moved from exploration to mineral processing. And then for my postdoc, I stayed in the same university, Delft University, by the way. And then I moved from mineral processing to management of mine wastes. So I've been moving through my career and also through the value chain. So I find it very interesting because I have had the opportunity to get like a nice overview about the full sector, how everything works on the different places, and what are the challenges and the opportunities that we as geologists have over there. I also have had the opportunity to make all the projects along in collaboration with industry. So even though I haven't worked directly in the industry, I have had a glance of how things work over there. So I think that gives me quite a nice overview to be able to do something and work towards a more sustainable sector.
Absolutely. And given your significant experience throughout the value chain, as you mentioned, we've seen mining companies declare commitment to carbon neutrality by certain dates in the future. Who should really be holding them accountable, and how might we accomplish that?
Yeah, well, the accountability is quite a difficult topic, maybe because there are a lot of powers moving along over there. But I would say that the main entity to hold companies accountable are governments. The creation of policies and regulations and clear rules on how to play the game should come from governments. I think those will be the ones making the biggest impact. But then governments is quite a maybe abstract entity sometimes. Then you need to be aware that the government is made by some people, policymakers, and they need to be informed in order to make those decisions. And they are also chosen by the people. So I think if the regular citizens, like now that we are becoming more aware of how things are, if we choose the people that we know that is going to guide those policies towards holding accountability and creating greener regulations, then the government will be able to enforce those the rules towards carbon neutrality.
I think it's good that we will maybe circle back later to getting people, geologists in as policymakers, because that's a very important point that you bring up. And also it might be idealistic, but perhaps shareholders can also too hold mining companies responsible. And we'll see hopefully that in the future. As a follow-up question, Karina, I'd like to ask you, what are the realistic and specific steps mining companies might take to achieve, a better carbon footprint? And what steps can exploration geologists undertake in our own work to mitigate any negative environmental impacts of exploration?
Thank you very much for the question. Coming from an exploration background, I would say that really involve your communities, because most of the communities, like most of the areas that I've worked in, have conservancies in them. And the communities know a lot about the environment that you are working in. So if they can also be involved in this, then they can also, let's say, help the companies to be accountable for whatever work that you are doing in there. Also working with the government. The government has policies, some policies in place, not everything in place, but they definitely need to step up and hold companies accountable for whatever work we do in this environment. The companies themselves, I would say we work really in an environmentally sound country. Also having worked in government in the Ministry of Environment, the Division of Engineering and Environment, there we've seen the effects of mining, let's say with the Tsumeb mine, the famous Tsumeb mine. We've seen the contamination in the surrounding area, and the government itself takes steps into monitoring the activities, both of active and exploration mining companies, just so that we don't have these situations coming up in future. So I would say engagement of the company with the government and the communities. That's the only way that we can actually curb this carbon footprint that we have.
Certainly, I think it's important for mining companies to start realizing that local communities and governments are their allies in that. That's a very good point. To move on to social responsibility, I'd like to ask two open-ended questions, and I hope that whoever feels most able to answer them will just jump in. First, why do you think diversity, equity, and inclusion is important for the mining and exploration industry, especially as it regards sustainable development and social responsibilities? And how can companies promote and increase diversity, equity, and inclusion?
That someone has to jump in right here. I can take it right. And just, anyone can react to what I'm going to say, but I think those are very, very important concepts. And for many aspects, I think diversity, of course, includes we are unique, right? So, and we all come from different backgrounds with different education and way to see things, right? So, and because the challenge we're facing now requires a lot of innovations and a lot of new techniques, a new approach to see the geology or to see the way we're going to extract those metals. And I find it very interesting, some major companies are hiring people with different scientific backgrounds, to solve a drilling problem, talking a biologist or or a physicist or chemist, how can you solve that problem? Could you just bring a new and fresh look? That's a good way when we can drive innovations and bring diverse background can help. The other side is more on the ground. You want to also include the local communities in your work because no project can move forward if you don't involve the local communities. So, and the easy way is just initiate discussions, get consent, and involve the locals to do work. Hire people. This is what Equity does. So we hire locals. Everybody needs a cook, needs exemplars, etc. So those people also know the land, so they bring a lot to the project. They bring the knowledge, but also they're part of it. I think that's the most important. And the last aspect I would add is just within your companies. You want, I think, probably relate to the first points. Diversity brings new ideas. and feel everybody comfortable. So wherever we're from, so and that creates like a good team spirit when everybody can say something and feel comfortable, and that's good for the company, and that's the key for success.
Thanks, Fabian. Anybody respond to that?
Yes, I would like to add something. I absolutely agree with Fabian, especially in the part that this includes engaging with stakeholders, local communities. So in the part we're talking about inclusion, but we also want to talk about equity. And that means changing a bit that mindset from the, normally exploration geologists go to look at the place a bit with let's call it a colonizing mindset. But when we are engaging with the local community, we need to see them as equals. They are not going to be the workforce at a lower level. They are just an equal part of the entire process. There might be also people in that community that are qualified in a high level to do the same job that we are now being trained to do. So I think embracing that part of not really saying we are going to work with the community, but really something more integrated and equal is essential for this to improve.
To add to that as well, I completely agree with Adriana and Fabian. And one thing that we also need to take into consideration is when we open mines in certain areas, then we must understand that some areas are completely underdeveloped, and we are bringing in certain developments and businesses that will cater to the mines. And this inclusion, also people will need to understand, what does this mean to them? We need to understand the needs of the communities and the effects or whatever comes off from that. Other businesses that might come off from that, and the change in their entire environment. So they need to be included from the beginning to really fully understand what's happening and not feel excluded when the project is all, when you are starting to mine, then they feel that they are outsiders now in their own environment, especially in terms of communities that have been living in those areas we are going into.
I think that's a really good point. And I think something that will be thematic throughout the discussion is that, at least in areas like in North America, one of the presentations was about Boulder, Colorado, which is in my backyard, and good luck mining in Boulder, Colorado, because in areas like that, you have a public perception of, well, mining might be necessary and mining might be fine, but it's not going to happen in my backyard. And so how do we actively change that public perception for communities like that we might live in, like that I live in? Feel free, anybody can respond.
I would say we need to also understand everybody's needs. So our needs, as Adriana said, we come in with a colonial type of mentality, but what I need from that community is not necessarily what that community would need from my mining company. So we need to understand what everyone wants in the end. We need to also always take into consideration that aspect, so that we don't have that mindset of not in my backyard, because now you are coming simply to take, and then I'm the one left with a hole in the ground.
Yeah, absolutely. It will be, challenging to figure out what the needs of different communities are, as you said, but it's very important. In terms of the next question, also open-ended, so feel free to chime in. When conflicts arise between mining and local communities over resource scarcity, for example, water, should geologists walk away from projects in the early stages before significant money is invested? Also, how does industry assess potential future problems which may not be present at the time of initial exploration?
Okay, so it's time for me to jump in maybe. So yeah, I think so. This is the case, like especially in like Chile. So water is really limited around the porphyry copper deposit, because those areas are also so famous for grape farming, maybe, I think. So, but I think, yeah, it's very important to be aware of any kind of potential risks at every point of mine development or exploration. So probably, so mining companies or exploration geologists should be thinking about any kind of potential risk at every stage of from the pre-feasibility level to feasibility level. So otherwise, so mining companies have to suddenly pay lots of investment to resolve those issues. So it's a really big issue. So I think the most important thing is being aware of or learning the best practice. So in that area, so as the time being, so to deal with any kind of the environment and local community related issues. Yeah, I think it's a key.
I think for every problem, there's a solution. So very early stage, I think, in terms of resources and needs. If you take water, for instance, so I think there is quite often like a solution to get some water, but you have to get agreements and talk to the locals if that solution is acceptable or not. So do you want like a drill a well or not, or getting like from like build the pipe or something, like, you know, there's like additional disturbance that might create it from that. But there's a pro and cons, and the cost should be like put in a balance. And as a geologist, I think you figure out pretty rapidly so the resources you're going to need, you know, in terms of access and resources for future development. So and that's something you should take into account pretty early stage for a business side for sure.
I think we had a question pop up in the chat, so I'll use that from Halleluya. How does technology impact the ability to effectively engage in communities? Are there any specific examples that you all have from your experience of new technologies or use of technology?
I guess one thing maybe that worked really well on projects I was working on was our ability to be sort of hyper-focused as to where we needed to work or double down exploration efforts using handheld XRF. So that was a really rapid way for us to assess the concessions, and then kind of rank and prioritize, and then obviously, I guess, try and use at the same time as we're looking at all the geological aspects, looking also at the cultural and social aspects. So mapping, you know, roads, villages, settlements, farming areas, sites of cultural significance or importance, etc., and being able to kind of assess that early on. Like was just mentioned, it's really important to be thinking about that from day one. And I think too, there's some other aspects of technology you can engage which are helpful. Like we used a man-portable drill rig on a project, which has a lower footprint and a much lower water consumption, but then also being cognizant that might reduce your footprint at the exploration stage, but then we still have those downstream considerations if you are going to move through to feasibility studies and mining.
I think that's a good point, and we might all, as geologists and exploration geologists, be aware of the different technologies that are exciting to us, but it's really about communicating those with the public as well, right? So if we have an alternative to cyanide, how do we effectively communicate that? I mean, cyanide is brought up so frequently as, you know, this very harmful chemical with lots of environmental damage and problems, and then we have a different perspective on that. So, I mean, I think as early career geologists, and certainly as everybody in the industry needs to focus on how we effectively communicate with our public communities, people that are not geologists, family, friends, and then in the wider community. And maybe there's a way for technology to do that. I'm not on social media, but maybe it's an opportunity. Certainly talks like this help. In terms of social response, Fabian, did you want to?
I just want to react. I think there was a clearly stated by Hugh Richard in his short videos. I don't know if you got it, but talk to your friends, talk to your family, and go back to school, you know, like your primary school, because nobody knows what we're doing in the field. It's just like, even in Canada, when people they don't know what the exploration camp look like and what we do and the damages, but also they ignore like all the things we do behind in terms of like mitigation plans, environmental survey, monitoring, and communication. So, and all the technology we bring. So it's not like just digging a hole and walk away. So it's no longer like that. So, and this is what we should emphasize, because this is not what we do, and there is miscommunication all the time. So So yeah, being a geologist is cool, but we do like a lot of other stuff around to make things better.
Yeah, I remember that part of the video montage, and I completely agree with you, because I even have people in my own family that have no idea what I do and are a little upset by it probably too. So I think that's our responsibility for all of us. In terms of social responsibility and risk management, how do we, like adapting to a changing climate? I want to talk about specifically how we address that. Let's see, that was my last question, I'm sorry. So moving on to career advice and mentoring, because I know that that's a big topic that we want to discuss. My first question is for Sarah. Academic research is essential for sustainable development and mining and for finding new mineral deposits. A major proportion of this research is carried out by postgraduate students and early career individuals. Do you think it's sufficiently valued and recognized by the industry, the society, or even academia itself? And if not, how could that be improved?
It's a really interesting question. I mean, yeah, I'm really passionate about being able to build bridges between these different worlds. So I think there's a risk that these amazing things are happening in university labs or in a more academic context, but they're not getting out into the wider world. But I think actually geoscience does a really good job of this in terms of industry partnerships or industry partnered projects. And there's some fantastic initiatives happening all over the world. But yeah, what I'm working on right now actually is really trying to address this issue. So trying to find deep science and technology innovation in universities and support those students or professors if they're interested to actually find a way to commercialize that technology. So partnering with mentors and investors and trying to create a startup. And we're starting to see that happening in the mining industry, which is interesting. There is a challenge of scale, I think, because a lot of, like, if you look at like tech or, the big companies are doing a lot of innovation in-house, but I think increasingly there's opportunity for smaller companies to emerge and try and build on these innovations and get them out into industry. Yeah, all about partnerships, I think, and yeah, building the bridges across.
Yeah, absolutely. And I think with academia, it seems, at least from my perspective, is that where the funding is, that's what determines the projects, at least that the students work on. And so maybe there's an issue here if we don't fund projects that not only look at where is more gold and how to get more gold, but also how to do that in a sustainable way. And so if anybody has any more knowledge on specific areas where this is being done in university, that would be great, because it seems a little bit like I see a lot of projects that are just, understanding the deposit and understanding how the deposit forms, but there's more to that the universities can research, I think.
I agree with that. So I just wanted to say, like, if you want to raise like money, like for your research, you have to communicate. So what's the goal of your project? And this is go back to, like talk to your friends or family and use like a simple language, as a training. So, and where is the impact or implication of your research for the society? So, and studying like a porphyry copper deposit is great. I think describing and documenting so the progenies and etc. is good, but what does it imply for copper supply? So this is like at the end is one deposit among the others. But I think like with some like the presentation like we watched earlier, so like explain like CO2 sequestration has a lot of impact for everyone. So that's the great technology, and how important like indium from the cassiterite is great as well. So I think you should be able to communicate to the public in addition to the industry to make an impact, I would say.
I think here I can talk from my experience. The projects I have worked with for my PhD and now for my postdoc are from European funding, from the EIT raw materials. And all those projects are consortia where you have academics, you have companies, big and small. That's a requirement. And the EIT really pushes hard for the results to go to a technology level higher every time. And they also push a lot for entrepreneurship. So you have the early career scientists say like, okay, what are you doing? And now how are you going to take it to the next level? Can you start creating your own startup? Or how are you going to integrate the work to implement it with a company? So I think if what we want to work is towards an actual implementation and not just a theoretical part or fundamental, we need to engage in those kind of projects that they are going to ensure that you are really collaborating with the industry in a way that the work that you are doing is going to really have some applications somewhere.
It's very exciting to hear that's what your experience has been in academia. Moving on, Subaru, my next question is for you. Economic geology is a global discipline that faces many challenges. Companies, universities, and consequently society benefit from employment and training of global talent. However, especially for recent graduates and early career individuals, it's difficult to get a job in another country, often because companies automatically filter out foreign applicants who don't already have work permits. Do you think that exploration and mining companies would benefit from removing such hurdles for early career individuals? And how else do you think international mobility could be improved for early career geologists?
Yeah, so I think, yeah, definitely, so there are some benefit for companies from removing the employment hurdles. So because the company can have more talent from different parts of the world. But I think at the same time, so it's not easy for the companies so to support for the new employees to get the working permits in foreign countries because of it's controlled by so the government jurisdictions, I think. So yeah, it's a difficult question, I think. So yeah, one example is actually, so I'm originally from Japan, but so my country, Japan, I think they have some restrictions for foreigners to get them the working permits. Probably, I think they need so 10 years, at least 10 years working experience to apply for the working permit. I think it's a really big hurdle for early career geologists. So, but I think the one option is so going to like undergraduate or so graduate school in different countries is a good option for all of the early career geologists. So not only for having international experience, but also for getting a chance to work in the industry in the country. So yeah, at some countries, I think once you graduate, so you can apply for like a fixed term working permit and can get some experience in the industry, I think. So that's why getting the first job is the most challenging part in your career. So I think it's a good option for everybody.
Yeah, I mean, I completely agree. And Subaru knows that I have experience working in Japan, and that it was hard for me to get work permit over there too. I think I should open this question up to Karina as well, because we have a lot of international experience on the panel.
Yes, I completely agree with Subaru. It is hard for a country to get in foreigners, not for a country, but for companies to get in foreigners ahead of the local workforce. But I also want to add that it would actually be good to collaborate with people from different countries and different bringing different perspectives to projects. That would be quite something to do, but it definitely, it's also a challenge that we have had, that you have foreign expertise, but you also have your own local people that don't have jobs. So you cannot overstep the government in this. You will have to go through that platform, and unfortunately it will have to come from them as well, but it would be good to collaborate.
Yeah, I think that there's an important balance there. Maybe, you're hiring people from the local communities for those mining jobs, but as Subaru said, because there's collaboration is maybe easier as a student, as part of a university. If you're able to have universities or mining companies bring students from different areas, then they don't necessarily need a work permit that requires 10 years of experience, but they can get experience in that country. So at least it was my experience, and that's a very good way to do it, I think.
That's absolutely right. And coming from junior exploration company, I think there's so much that can be done on, let's say, even our grounds that we are working on. There's a lot of areas that haven't been worked on before, where you can do quite a lot of scientific studies. And that just requires bringing in students, and they can, even those students already at that level can collaborate with the universities that are here and just work on the project. And that opens up, data sharing, let's say. This is also something that we were discussing this week at WITS. Asine from the Council of Geosciences actually brought it up, that how do we collaborate together? He worked on a project in West Africa, and he was saying, how do we bring such expertise that we collaborate, that we share data? It's from a confidentiality perspective of companies, it's hard to share data, but a country like Namibia, where you have a lot of outcrop, you can do so much on geology, and even just to understand the structural controls on mineralization in these areas, which helps the mineral exploration companies in the end.
Absolutely. And I think that it's important to bring up junior companies because, I mean, in some ways, you have junior companies that don't invest in student research. And then in others, you do, and you hear very exciting collaborations between the two. So it's important maybe because it's easier to approach junior companies that are a bit smaller than, say, a large top 5 company with a project that they could fund. And if you have sharing of data, you don't necessarily have to have everybody out at the same outcrop, reinventing the wheel. They don't have to all figure it out for themselves. Right? We can share that information.
Yes, definitely.
In terms of specific advice, I want to ask Fabian, what non-technical and social skill sets and knowledge do you think is important for aspiring economic geologists to ensure that they're doing their part for sustainable development and are successful in regard to compliance with those ESG factors? And how does that maybe compare to, what was expected from geologists in the past?
Well, I think I mentioned a little bit about that earlier. Once there's a few geologists right now, some that not only focusing on geology, but nowadays, but also a multitude of other components that's like we have to deal with. Like they design the field program, organizing the logistics, hiring new staff, so getting new permits, and also talking to local communities, biologists, etc. So this is all like a soft skills in terms of communications, managing people, and getting things done. So, and having a strong technical degree, I think helps like to provide the, I would say like kind of support, like because you need like to find a deposit at the end, but there's like many other aspects. And one of the key, I think, something you can try to practice and through like the student chapters, like leadership. This is what it's meant, like working as a team, organizing an event like today and doing things together, like dealing with the budget, dealing with the timeline, dealing with tasks, and dealing with other people around, and don't stay focused on your thesis like all day, every day. So I think the SEG does a great job with that, and I have to take the opportunity as a student to practice those skills because they're going to make a big difference later on. So and once you switch in the industry, you're going to learn more about like health and safety protocols and how to talk to local communities, but that comes later.
Yeah, absolutely. It plays really well into public perception and how we deal with that. You can't necessarily just live in your research or work bubble. But in terms of public perception, I think we've talked about this a bit before. But how do we make mining more well understood? Do you feel like it's well understood in your communities? I certainly don't think it's well understood in mine. Adriana, what about you? Do you feel like mining is well understood where you are? Is geology valued and appreciated by the local communities? If not, how do you work on that?
No, I would say it's not well understood. For this, I can talk more than as a geologist, as a Colombian citizen. So where I'm on the other side, where the exploration projects go to the place, there is quite a strong campaign anti-mining, the oil industry as well. And there are some quite hardcore environmentalists, and some people are misinforming quite a lot. So yeah, people are quite reluctant on allowing any kind of project in their lands because they just don't know how things work and they don't have this awareness that we do need minerals. And I think what we need to do about it is something, a word that has come quite often in this panel now, and it's communication. We need to learn how to communicate with people, how to tell them, how to teach them. We don't need to convert them from one day to the other. And that is what you learn with these soft communication skills, that you cannot impose your point of view and say like, yeah, I am the geologist, I know how this works, and then you need to believe me just because I am this super knowledgeable person. But you need to learn how to communicate with people, how to tell them and teach them what you know, the knowledge that you have, and understand what their priorities are, their concerns are, and try to make a bridge over there. And I think a key in this is what was also mentioned before. We need to spread the word in our normal groups, with family, with friends, if we engage in any sort of social media, blogs, whatever. Whenever we have the opportunity to share the knowledge that we have in an easy way that people can really take it and start understanding and getting engaged. I don't know, maybe some of you know programs like Skype a Scientist or Girls into Geoscience. These programs where you can every now and then communicate with communities or with schools, or just get everywhere where you can and start spreading the word about the better work that we are doing now.
I'm glad you brought that up, and maybe you can pop the two societies that you mentioned into the chat, and then maybe link them and people can check them out. Fabian, go ahead.
To add to what Adriana was saying, sorry.
Oh no,
I was speaking over each other.
Yeah,
okay.
Yeah, you.
Okay. To add to what Adriana was saying, yes, it's definitely a challenge. We are working in the Kluane region of Namibia. This is where we have the Himba community. Everyone knows the Himbas. These are people who haven't gone to school, and it's really hard to explain what exploration is. So I'm just speaking on exploration. And in terms of, we go into a certain area, we look for, let's say, copper. We find a little copper project, we work on it, and as soon as the copper price goes down, we have left onto the next project where the price, where the prices are reasonable, or where we can make more money to work. So, and then when the prices again of copper come up, then here we come back. So what the Overhimbers normally have going is, we come, we drill, we take their rocks. Next time we come, we are having still cars and things like that. So they feel we are stealing their rocks and going to sell them and coming back with a car. This is just a thing of, they don't understand what exploration is. So I always thought that if someone can come up with even a video, because people like to see, which can be adjusted to a community like the Kluane region, where they can see, okay, this is exploration. This is how long exploration can actually take before you develop a mine. Because they can never understand, you have been here for a year, you took out rocks, you come back, you still haven't found the mine, you still haven't opened the mine. And when we come in, then we'll say, okay, this is the stages of exploration. If there's a mine that's opening, this is how the community can benefit. But those benefits that are not coming to the community is what also brings about a restlessness and what do I say, these bad feelings between the two, the exploration company per se and the community. So we really need to understand what's important to other people, because it doesn't speak to what's important to us.
That's a really good point. And I know that I'd like to get Subaru's perspective just on public perception and mining in Japan, because I think it's actually a pretty unique one.
Yeah, so yeah, I think in Japan, so in general, so it's my opinion, but I think so mining is regarded as really dirty and really so dangerous and so environmental harmful so industry from sun so history of environmental pollutions, so which we learn in the school, so high school, junior high school, but they don't learn where or how mining is doing now. So I think now mining is really environmentally conscious. So yeah, so they usually do really care about rehabilitation after mining mining is stopped. But yeah, so I think the outreach is really important. So yeah, especially like a country like Japan. So yeah, how the mining is now going forward, or what mining is doing after they end production. So yeah. As Fabian mentioned, I think communication is really important.
I would just add to what you just said, and Karina also mentioned it. So I think people are not aware of the timeline of the exploration. So it's not because you take a soil sample, you're going to open a mine tomorrow. Most of the time we walk away forever, because there's nothing interesting and enough. Or if something is interesting, it's going to take a long time, just to do the due diligence and just get a plan, just in concrete and make things happen, but get a consent for everybody. So I think, yeah, we talk about years, not days. So, and again, back to communication. So.
I think circling back, it's important to talk about, Adriana mentioned this, how do we get knowledgeable people in as policymakers? So how do we, when we're trying to bring in the governments, how do we get geologists who might be gravitate more towards working in industry than to maybe take a different career path and move into policymaking? And how do we increase that communication in that way? If there are any specific suggestions, that would be great, but otherwise comments are good too.
I think we don't necessarily need to become policymakers. We need to talk to them, and we need to learn how to speak to them. In academia, that is where I move the most. We tend to go super I know a lot, and I want to let you know the technical details and names of minerals, chemical reactions, everything. That's not what I care about. So we need to learn how to communicate with them. What are the points that they want to listen to, so they can take our message to the ones that are actually making the decisions. So I think that's the key. There is also the option of geologists becoming policymakers. If you don't want to go to a field, but you start more like a different, more bureaucratic career, that is also great, because if you have someone with the science knowledge on the other side, then there is also more empathy. But yeah, I think, again, communication is key, but then now is a different kind of communication. And there is plenty of training for that. It's something that you really need to learn as a second skill, or even another career path.
Yeah, I think that's a really good point. We're sort of at 10 minutes now, and I want to encourage everybody to continue to stay for our concluding remarks, but I'd also like our panelists to just provide like a brief wrap up vision for the future, and I guess what they'd like to see happen in the larger economic geology community. And I'll start with Adriana, because I forgot you the last time and I feel a bit bad about it.
Okay, well, I think like my dream about how the sector should be is that we reach a point where we can actually mine without leaving the impact, so that we become carbon neutral, super sustainable, that we don't create waste, that we leave the land in the same or even in a better way as we found it before exploration. Like that will be the ideal world. But we are quite a long way far from it. And I think one of the issues for doing that, like in research, there are advances on technologies and methods, and there are ways for doing things better. I think that the problem is that the industry is way too conservative and moves very slow. So we need to find a way to make it real quicker and embrace all those things that we are proposing. So at some point, we start implementing those changes that actually make the industry actually sustainable.
I completely agree with you that this industry moves slowly. That's a very good point. And I don't want to follow up on everybody's points because they're all good. But next, I think, Fabian, your concluding remarks.
Yeah, probably will address directly to the students who are still here, talking about because they need an answer right now. I think talking about the 40 years in the future, so it's in their hands. But I think the first advice I would give is just use the SEG platforms as much as you can. There's much to do. We're gonna have talks, webinars, mentoring program. This is the way that all of us can just jump in the mining industry. And with our vision that we developed today, just make things happen, but you need the first step, and I think that's the most critical and something that my committee has been working on, and just we want everybody to be on board, right? And don't be a leftover. So in your country where you are, don't feel stuck. And at the end, so we all go toward the same direction. So to get more transparency, but we have to accept that whatever we do, we're gonna disturb the land, but we also have to measure our impact, and accept there are some people and species living there. So, and for every disturbance, and everything we want to do is just make a plan, mitigation plans, and think about reclamation. So we need more resources, we are more and more, but yeah, we can do that in a better way.
Karina, how about you?
I would like to see rather a balance as well between a capitalist nation and socialism. I see a lot of, when we've been discussing or even having listened to session one panelists, we want inclusivity, we want collaboration. So more social interaction between the people is a bit difficult with COVID-19 at the moment. But I would also like to encourage that the young geoscientists actually attend excursions or talks once we can all socialize again, because these are the networking platforms. Like our community here, our community in Namibia, actually I'm not in Namibia at the moment, our community in Namibia is quite a small geological community, and when you're on excursion, you are sitting next to exploration managers, mine managers, and these are great networking platforms for young geoscientists. So to just attend those, and it's also a foot in the door, I would say.
Yeah, I absolutely agree. Subaru.
Yeah, so yeah, I think, yeah, so everyone in this discussion, so pointed out a really good point. So raised really good point, I think. So, but I think we are seeing the big and drastic change in our economy. So towards low carbon or carbon-free economy, I think it's a really big change. And as mentioned earlier, so in the previous panel discussion this morning, so I think so anyway, so mining itself is not sustainable. I think it's a really good point. But to accomplish sustainable development, so anyway, so we need to refurbish lots of the machines and devices. So now already in use in our current economy. So then that's why we need lots of raw materials to change them to low carbon, footprint devices and machines. So as an economic geologist, so if I can contribute to society, and the public, so yeah, I think it would be my pleasure. So working as an economic geologist.
I think that's a nice hopeful note to end things on. Stay tuned for our concluding remarks. And I just want to thank all our panelists very much for joining.
Thank you.
Thank you, Doran. Thank you, everybody.
Thank you.
Thank you.
Yeah, I would like to say a few things to wrap this session up before we play a longer montage of all of the perspective videos we got to lead out of the session. First of all, I would like to express our gratitude to all our speakers and panelists. Thank you very much for your valuable contributions. This just has been a very interesting and great discussion, and I really enjoyed it. And thank you very much to Lauren also, who did a really great job at moderating. And I would also like to thank Helen for sharing the earlier part. I would also like to thank everyone for attending. I hope you enjoyed this session as much as I did. And I would like to extend special thanks to everyone who sent us perspective video clips with their backgrounds and thoughts. We received almost 2 hours of material. And please check out the full contributions on our YouTube channel. These videos are a wealth of interesting stories, valuable advice, and important perspectives. And we will post a link to our YouTube channel in the Zoom chat again. For those of you in the SEG or interested in joining the SEG, I would like to draw your attention to the work of the SEG Early Career Professionals Committee, which is shared by Fabienne, who just has been on the panel. Please check out their website at zegweb.org/ECP and reach out to them with questions and suggestions. And again, please also check out their videos on our YouTube channel. They offer really useful advice and present very valuable thoughts. And the SEG ECP committee also coordinates the SEG mentoring program. And if you're interested, I encourage you to go to the mentoring website at zegweb.org/mentoring. Just to highlight a few upcoming SEG events, the University of Las Vegas SEG chapter hosts an epithermal ore deposit short course on Saturday, and the details are on the SEG website. We ourselves will be hosting a lecture on Thursday in 2 weeks about the Kupferschiefer. And if you would like to attend that, just drop us an email. There's also a Students and Early Career Professionals Mentorship webinar coming up also on the 6th of May. Again, the details are on the SEG website soon. Then there's an SEG, SGA, and Ore Deposit Hub's Exploration Career Kickstarter, for which you can find more information on the Ore Deposit Hub website. And there's another great initiative by another student chapter, the University of Toronto SEG Student Chapter, who hosts a student chapter virtual field trip competition, where student chapters can submit short videos about outcrop, which is related to economic geology, in order to have like a shared field trip experience across student chapters. And I think there are quite substantial monetary prizes involved with that. So check that out. And the submission deadline is at the end of July. And to conclude, I would just like to highlight that the abstract deadline for the SEG 100 conference is coming up, which is the 3rd of May. And you can find more info at seg100.org. We hope the SEG Student Chapter's Earth Day Symposium could become an annual event, and each time hosted by a different chapter. So please have a thought about whether you and your chapter are interested in hosting next year's event, and get in touch if you have any questions. And just to highlight again, the symposium continues on YouTube. Please check out our channel. Everything you saw today will be there as well as the technical talks and panel discussion from earlier this morning, as well as the perspective clips in full. And to conclude, we will play another video montage, which kind of showcases the great contributions we got. So thank you very much for attending, and have a good evening, afternoon, or morning. Goodbye.
Hi, it's very nice to meet you in this video.
Hello, everyone.
Hello.
Hi.
Hello, everyone.
Hola.
Hello, everyone.
Hey, guys.
Hi.
Good day, everyone.
Hello.
Hi.
Hi, everyone. Hello, everybody.
Hello.
Hello, everyone.
Hey, everyone.
Hello.
Hey, everyone.
Hello, nice to meet you.
Hello, everybody.
Hello, everyone.
Hi.
Hello, everyone.
Hello, everyone. It's a pleasure that you are watching our video. My name is Luis Alberto Pisano.
Hi, I'm Charlotte Clark.
My name is Paul Sonia Castillo.
I'm Audrey.
My name is Sarah.
Keshi Sitembi. Giancarlo Daroch.
Hi, my name is Fernanda Alvarado.
My name is Zhang Xin.
My name is Doran.
Meu nome é Lúcio Massari.
My name is Hugh Richards.
My name's Ella Losberg.
I'm Gaura Baeva.
I'm Gabriel.
My name is Alanis Olishbert.
My name is Mars Marv.
My name is Isaac Simon.
Ino Thomas.
My name's Aaron.
My name is Chu Xianghan.
My name is Denis Echoki.
I'm Ada Rodriguez.
Molly Ag.
Conde Wells.
My name is Renata Barros.
Fiona Best.
Benjamin Larenas.
Mary Barton.
Dan Smith.
My name is Zheng Xi.
And I'm Liu Tao. And we are the first year graduate student of the Chinese Academy of Science.
I'm an undergraduate geology student from University of Barcelona.
From SEG Student Chapter, YGG class.
I'm an MDRA student at the University of Leicester.
With UNAM and also part of SEG here in Namibia.
Final year student at the University of Namibia.
Eu estou prestes a me formar em Geologia pela Universidade de São Paulo.
I come from SEG Student Chapter and IGGCS.
I'm the Vice President of the Student Chapter of Barcelona.
I'm from Brazil. I'm Master Student at University of São Paulo. I'm also the President of the SEG Student Chapter here.
And I am a PhD student here at Monash University.
From the University of British Columbia in Vancouver, Canada.
And I'm a student from SEG Student Chapter at IGGCS.
I'm a fourth year applied environmental geologist here at the University of Leicester.
I'm doing my Masters in Applied Geoscience at RWTH University.
Hi, we're both studying at the RWTH Aachen University in Germany, and we're both studying applied geosciences in our masters.
And I am a final year student at the University of Namibia doing a honors degree in geology, and I'm also the SEG Student Chapter President of the year 2021.
And I'm an exploration geologist based in Santiago, Chile. I'm also part of the Early Career Professionals Committee.
I recently returned to academia as a PhD student at Colorado School of Mines in the United States.
And I am an exploration geologist based in the UK, working for Nordgold out at the Bisibuli open pit gold mine in Burkina Faso.
And I'm an economic geology PhD student at the University of Leicester, studying the emplacement of the Northern Bushveld complex.
My research direction is porphyry copper deposit in the Central Iron Orogenic Belt.
I'm currently doing a research project on the potential of 30 style nickel, copper, platinum group element sulfide mineralization in the Kalahari zone, Botswana.
And I'm majoring in or specializing in economic geology and petroleum.
And I'm studying on how to evaluate the ore-bearing properties of pegmatite in the Himalaya orogenic belting now.
I'm a PhD student at Monash University. I'm focusing on the transport and source of rare earth elements. Rare earth elements are really important for the future. They're used in wind turbines, they're used in electric cars, and Australia is full of them. So what I'm studying is how exactly these rare earth elements, where they came from, how they got to where they are.
The field I mainly study is rhenium in porphyry. The problem I want to solve most is the beneficiation mechanism of it and where we can get it.
I am a PhD student and my project is about modeling igneous intrusions for 3D modeling software. And the idea is to improve how we are modeling the subsurface for resource management.
My project is to investigate fluid rock reactions, especially the feldspar water reaction, especially key feldspar reaction and albitization reaction, because key feldspar and albite are always associated with IOCG deposit and porphyry deposit.
My research at the moment is based around deep eutectic solvents, which are a more environmentally friendly way of processing gold as an alternative to cyanide.
I'm currently working on my master's thesis, which is unraveling the Cretaceous and Cordilleran deformation related to the McMillan Pass shale hosted massive sulfide deposits such as Tom and Jason, which you can see behind me.
My current research is rare metals. I would like to throw my own research on the status quo and the prospects of rare metal mineral resources in China. to make an assessment.
I'm studying environmental petrology, which is basically making rocks, and I'm interested in putting critical metals into my experiments to see how they behave in deep earth conditions. Basically, how do critical metals move from the subducting slab into the mantle wedge? And hopefully that will give us an idea of how to figure out where and why they form eventually in the crust.
My certain research direction is a study on the genesis of sedimentary air deposit. To a certain extent, the study of such deposit can provide more evidence support for the evolution of the Earth's atmosphere and the development of life.
My current research direction is light rare earth mineral. I mainly want to solve the problems about the genesis of the deposits, including the source of all forming materials and the source of fluids.
My main research direction is carbonatitic alkaline-related rare earth element deposits. Many countries consider them as strategically important resource. So in the future, I want to characterize magma source and all forming fluids.
My first motivation to be involved with economic geology, I would say, is that Brazil is a huge country with a lot of unknown potential. There's still a lot to study, a lot to discover around here.
I'm very passionate about geoscience and in particular economic geology, more so because it's a field that allows you to constantly engage with the build-up and structure of our planet Earth.
I want to become an economic geologist because I love geology, I love minerals, I love nature. It's all about love.
Meu interesse por mineração, geologia econômica, exploração mineral começou por causa das disciplinas ofertadas na graduação. Tive a oportunidade de estagiar no Serviço Geológico do Brasil, na gerência de recursos minerais.
I had a real passion for research and really enjoyed it, but I wanted to make sure that the research I was taking part in had wider implications and would influence the decisions of companies and the industry I was working within. And I feel like being part of the economic geology industry is a perfect way to achieve this.
My big interest is to contribute to make geological data more accessible and therefore properly used.
I chose to be an economic geologist, and it's interesting. It makes me feel that the development of my career is closely linked to the country.
My journey into economic geology began in my first year at the university, where we would be taught of several mineral deposits our country was rich in. Specifically, minerals like gold, lead, copper, zinc, and tin. So we would learn about these subjects, and I'd be very interested because I would think
economic geologist. I love being an economic geologist because I get an opportunity to
use to find these metals.
As we all know, mineral resource is an essential factor affecting the national development. So the interest and the importance of it caused me want to be an economic geologist.
I studied geology and wanted to be a geologist because the mountain is near. Even you don't climb it, it's always near. When we looked up at the vast starry sky while standing on Star 2, I think it's really romantic to spend my short life exploring the everlasting gifts of the earth, rather than ups and downs of happiness and sorrow in a single day.
There is a proverb that says, if there is a career that you are willing to work for the rest of your life and never regret, then it's your calling. For me, economical mineralogy is.
As for me, it's a pleasure to be a member of Economic Geologists. It's a really nice chance to leave something meaningful to this world.
For the future of the economic geologist, I think it will
that we are helping people understand not only where, but how we extract the metals that they use every single day in their routine lives. And if we can do so across the world using our own networks, we then be able to communicate and broadcast this message across a wide spectrum of people and on a global platform.
I look forward to using my skills to make the world a more sustainable place, and especially assist in responsible use of my mother continent's rich resources. Thank you.
Thank you very much and stay safe.
Thank you, everyone.
Thank you.
Thank you, everyone.
Thank you very much.
Thank you very much.
Thank you.
Thank you.
I thank you so much for taking time to listen to this, and have a good day.